Hi, IM3 students. In this video, we're going to learn about 5.3, the graphing of cubic functions. So we're going to get into one of the famous polynomial functions, which is the cubic function. And we're going to take a look at how the cubic functions will be transformed by applying certain characteristics to the equation. And so let's note that the general equation for the cubic function is given right here. So it looks exactly the same as the quadratic one, except that it has a cubic instead of a square. So we will be actually looking at transformations and predicting transformations according to the way the function is given. And here is some recall information. We call that the standard form of a quadratic equation is this way. It's this one right here, f of x equals ax squared plus bx plus c. And then the standard cubic function is this one right here. And the parent cubic function, which is dropping everything in the back of the general equation, just only taking at the most basic function, is f of x equals x to the third. So just like the x squared function, there are certain points that make up the cubic function. And these are the points that we are going to take a look. So when x equals -2 and we apply the cubic function, basically it's going to be -2 cubed, which gives us a -8. And notice that point is found like over here somewhere. And then when we let x equals -1, we cube that, we get -1, and notice that point is like right there. And when x equal to 0, we got y equals 0 cubed, which is still 0, and it's right there. And when it's 1, we cube it, we still get 1, and it's like right there. And then when we cube the 2, we actually get 8, which is right there. And what do you guys notice about those points once we connect it? Voila, it makes the actual the skeleton for the cubic function. So this is what makes the cubic function looks like this. It's driven by this set of points, and we call these points the reference points. So we have a new set of reference points for the cubic function, and that this is how they're obtained strictly from the function y equals x to the third. And that is what we will be taking with us when we talk about the parent cubic function. So here it is again. And let's take a look at some characteristics of the parent function. So here we have the cubic function, looks like the sideway n or s, like a snake. And then the 3 reference points, because 5 points is a little bit too many, so we're only going to be working with the 3 basic points for the reference, which is -1, -1, 0, 0, and 1, 1. Notice the more points we have, the more detail we will have. But just for the sake of reference points, we're just going to use the 3 that are closest to the origin, which still gives us a kind of basic shape of the cubic function. So those are the 3 points, and let's just remember that for the sake. And it actually looks almost exactly like the square, except for the signs here that are negative, both of them. The domain, as you can see, which means the graph extends both ways, to the left and to the right infinitely. So that's why it is all reals for the domain. So let's just remember that the domain for the cube function is always all reals. And the range, as you can see, it still goes up and down infinitely. So the range is actually also all reals. So same thing as the domain. So domain and range is all reals. That's easy to remember. End behavior, I'm going to take a minute to explain. End behavior is what happens when the function all the way at the end of time. So to describe the end behavior, we always use, as x approach the positive infinity side. So in case you do not know, the positive infinity side is on the right-hand side. So if you think of the right-hand side as you approach the right-hand side as positive infinity, and then as you approach the negative infinity is the left-hand side, then you can think of it as you go to the right of the graph, where is the graph going? As you go to the left, where is it going? So as you can see, this is the function that's being graphed. As you go to the right, it's going to point upwards. So the end behavior, the function is going to be at positive infinity as you go to the right. And then on contrary, when you go to the left side, the graph is pointing down, which means it's going to be going towards negative infinity. So what that is called is an end behavior, which means at the end of time, what is the behavior of this function? And so that is kind of in a nutshell what is the end behavior. The zero of a function, so basically it's saying, well, where is the graph touching zero, which means the x-axis. Where is the graph touching the x-axis? Well, there's only one point here that the graph touches, which is at x equals 0. So that's only 0 for this function. And where the function has positive values, well, that means just, if you actually draw a line here, consider the top part a positive and the bottom negative. Well, anything above this line is going to be positive. So the x values that point to that is actually anything to the right-hand side of the graph is considered positive, correct? Which means we're looking at this piece right here. So this piece is going to be the positive value. So how do we describe that using x? That's going to be when x is greater than 0, meaning to the right-hand side of the y-axis, right? And then where does the function have negative value? Well, here's where it's negative. As you go to the left side, that's where it's going to be. So x is less than 0 to the left side. So this is the right side. This is the left side, where the graph is going to be positive and negative. And where is the function increasing? Increasing means it's going up. As you can see, this function keeps going up throughout the entire graph. So there is no point where this graph is going down. So it's always increasing, as you can see. It's always going up. So that means all reals. That's everywhere. It's all reals that it's increasing. Where is the graph decreasing? Well, it's not going to decrease anywhere because it keeps increasing, so there is none. And is the function odd? Yes. Remember, an odd function is when you actually substitute negative x into the function. So if I evaluate negative x here, I'm going to have negative x cubed, and I will get negative x cubed. So if you have a negative of the original back, this is an odd function. And also an odd function has symmetric across the origin, which is right here. So it's symmetrical. So this is definitely an odd function right here. And again, this is a recall of the information that was given previously. The general equation for a polynomial, we were working with the square earlier, and now we notice that the only thing difference between this equation and the one that we have learned before is that there's a cube instead of a square. So the same equation, which means the transformations will be the same. So A is going to give you vertical stretch or compression, depending on if it's greater than 1 or less than 1. B right here is going to tell you a horizontal stretch or compression basing on the number. And remember, B is always the number underneath the 1, the fraction. And H is going to tell you whether it's going to go to the left or to the right. And then K is going to tell you whether it's going to go up or down. So now that we have reviewed our general equation, let's take a look at some actual equations that will tell us whether what the transformations are. So we're just going to only identify the transformations from the parent function to the new described function. So remember, the parent function is x cubed. So now we're looking at the new function. So g of x is based on these transformations. We notice that there's an a right there of 2. Since a is greater than 1, there's going to be a vertical stretch factor of 2. And based on this right here, remember, plus means to the left. So we're actually going to move 1 unit to the left. And then based on the number k outside, so this is h, this is k. K is negative, so we're going to move 2 units down. And that would be all of the transformations. There are 3 things that are going to change the outlook of this graph. Next, we're going to look at g of x here in the next question. And notice that we have a negative sign, a negative 1/3. So there are 2 things here. First, a negative outside indicates a reflection across the x-axis. Also, because of that 1/3, that's a, the value of a is less than 1. So there's going to be a vertical compression factor of 1/3 as one of the transformations. And then 2, a minus 2 indicates that there's going to be a 2 units shift to the right. And then finally, a plus 1 in the back means 1 unit up. And those are the transformations here. With practice, you're going to get better at describing the transformation. So that's a beginning. And I'm going to have you guys try this right now. So we're going to do some of these problems together. Write the equation of the transformation function from the parent function. So we're going to be describing this, and we're going to call the new function g of x. So we're going to call g of x, and we're going to write the equation according to the transformation. It says that it's reflected across the axis. Well, we know that to be reflected across the axis, there will be a negative in front. And then it says translate it 4 units up and 5 units to the left. So to the left means we're going to actually have x plus 5. Remember, the parent function is cubed, so we're going to have the cube right there. And then going 4 units up, that means it's going to be a plus 4. And that would be the g of x with the transformations described. Number 2, g of x is now stretched vertically by a factor of 3. That means a is going to be 3, so we have 3 in the front. It's also translated 5 units to the right and 2 down. So we're going to have x minus 5 because minus means to the right. And again, this is a parent function, so it's going to be cube and then a minus 2. So it's 2 units down. And that would be the parent function translated and using the transformations, creating the new function g of x. Lastly, we're going to have g of x stretched horizontally by a factor of 1/2. Remember, horizontally means it's going to have a 1 over factor of 2, so it's going to be 1/2. So it's horizontally stretched. Again, it looks like it's a fraction 1/2, but it's actually a horizontal stretch. And then we have 3 units to the left, so we have x plus 3 and then cubed. Okay, so that would be the new function with the transformations. What do you need to know about the parent function? So we already discussed that these 3 are the reference points. So this is going to help us with the transformation applying to the general equation here to help us obtain the transformations. And I'm going to show you a system of how, again, to utilize the equations with the x and y using the reference points and applying those transformations to the reference points to obtain the new equation. So here we go. Taking a look at the first example, we're given g of x is given by this equation right here. And then if we map it up to the general equation, we will be able to identify a, b, h, and k. So part A, identify the transformation. So again, just like what we have practiced earlier, let's go ahead and name some of the transformations. So first thing, this 2 is actually inside one pair of parentheses. So notice that A is actually 1. B is actually inside the second parenthesis. So what makes a 2? So this is a little tricky. As I have stated before, don't be fooled by the number. So to obtain a 2, you actually have 1 over, because remember, B is always underneath a 1. So what does B need to be in order for this number to be 2? B is actually equal to 1/2. That is going to give us a 2. So just think reverse order. And so we have actually because B equals 2, which is less than 1, we have a horizontal compression of 1/2 factor. And the next thing is we have a x plus 3, which means we're going to have a 3 units shift to the left. And then finally, plus 4 means we're going to move 4 units up. And the next thing is I'm going to use these transformations to help me identify the 3 reference points. And remember what the reference points are, right? For a cubic function, it's -1, 0, 0, and 1, 1. So those are the reference points, remember? And we're going to write the equations here. For the x, anything that goes inside would be related to x. So we have b is 1/2, so it's actually 1/2 x. And then we're moving to the left, so it's going to be subtracting. So remember, moving to the left is subtract, to the right you add. And so it's 1/2 x minus 3, and then the equation is actually, we're going to, let me show you guys a quick way to actually name the y equation. For the y equation, if you read everything, you already applied this to the x. So this is x. So we're going to read this as y equals y plus 4. So it's going to be y plus 4 is the equation. Okay, because we already applied the x over here, so we don't need to worry about it. Let's go ahead and use the x and y values so x values are the first numbers in the parentheses. So it's going to be 1/2 of -1 minus 3. That's going to give us -3.5. And then 1/2 of 0, which is 0 minus 3, that's a negative 3. And 1/2 times 1 minus 3, that's going to give us negative 2.5. And then the y values, we're looking at the y, so it's going to be negative 1 plus 4, that's 3. 0 plus 4, which is 4. And 1 plus 4, which is 5. So these are the new coordinate points that we're going to graph. So 3/2 and 3 is like right there. Oh, I'm sorry, it's negative 3/2. So negative 3.5 and 3, which is right there. And then negative 3, 4, negative 3, 1, 2, 3, 4. And then we got negative 2.5, 1, 2, 3, 4, and 5. So here is my 3 points of reference. After the transformation, this is where they would end up. And so if I just follow the same shape of the cubic function, it should look something like this. So it looks like this graph has been horizontally compressed by scale factor of 1/2, and then shifted 3 units to the left and then 4 units up, and this is the new location of the graph given those transformations. Hopefully you are more familiar with that now. Let's go ahead and move on to practice. So you may want to pause the video and try the problem on your own before you actually look at the solutions. So here's another one. We're going to start by naming the transformation. Again, a negative in front indicates a reflection across the x-axis. So that's the first transformation we notice. And notice that comparing to this equation, b is actually equal to 2. So that's what b equals. And because 2 is greater than 1, it's a horizontal stretch factor of 2. And the next thing is it's going to shift 3 units to the right, okay? Because minus 2 means to the right. And remember, to the right you subtract, to the right you add, to the left you subtract in the transformation equation. So we're going to actually apply those to the reference points. So here are the reference points for the cubic function: negative 1, negative 1, 0, 0, and 1, 1. So those are the 3 reference points again. And we're going to get the equations now. So let's take a look at the equation. Anything that has to do with the x is within this right here. So since this is a always goes with the y. So x is anything with the b. So there, b is actually 1 here. So we only have the 3 units to the right. That means x plus 3 is our equation for the x. And then y, we're going to read everything here as y. So it's negative 1/2 y, and that's what the y equation looks like. And we're going to use that to transform the reference point. So negative 1 plus 3 equals 2. 0 plus 3, that's 3. And then 1 plus 3, that's equal to 4. And then for the y values, that's going to multiply by negative 1/2. So that's negative 1/2 times negative 1 is actually 1/2. Half of y, that's 0. And then negative 1/2 times 1, that's negative 1/2. So we have the 3 new points, 2 and 1/2. So 2 and 1/2 is like right there. And then 3, 0 is right there. And then 4 and 1/2, which is right there. Negative 1/2 it should be. It should be negative 1/2. So 4, negative 1/2. So notice that this is where my new graph is going to be, and here I'm going to try to again make it into the S shape, and here it is. Notice that the graph is reflected across the x-axis, and that's what it looks like. And then there is a horizontal stretch factor of 2, and then 3 units to the right, and this is the new graph. So hopefully that is more practice for you. It is time for you to do some homework assignments and practice the skills that you just learned right now, and go ahead and get started with the homework assignment that is found in Google Classroom. Have a good day. See you next time.